So let's consider what would happen if we had a charged particle and it was moving and we had crossed fields. So, for example, let's imagine that we have a charged particle Q right here, okay, and it's moving at some velocity v. It enters a region of space here in which there is positive charge, negative charge, and so there's an electric field like that. So what's going to happen is when it goes in here, it's going to deflect. We did a problem like that earlier on in the semester. But what if there's a magnetic field? Okay, so if there's a magnetic field, then what would happen is, let's say we have a magnetic field into the page. So we've got a magnetic field that way. That means the magnetic force is that way. Okay, so the two could cancel and the particle would go straight. Okay, so we would say, what would make it go straight? Well, that would be if the magnetic force, the magnitude of the magnetic force equals the magnitude of the electric force. So QVB has to equal QE. Well, the Q's cancel, and we find that the V is just going to be equal to E over B. So not just that they have to balance, it turns out that no matter what they are, there's a particular speed at which these things will go through. Now, this turns out to be very, very important because now, suppose that you were wanting to actually build a device that had a beam of particles. So, for example, you remember we had talked earlier in the semester that you could have like a beam of protons or something and then put it through an electric field and deflect it. Well, yeah, you can. But all the protons would deflect differently if they're going different speeds because they'd spend a different amount of time in the electric field. We would use that for like proton therapy for cancer treatments. There's also epitaxy or depositing of things into semiconductors, but you need to be able to direct the protons where you want them to go. You can't do that if they're all going different speeds. Likewise, cathode ray tubes, CRTs, the old CRT TVs, the way that they worked was you had a beam of electrons, that's the cathode rays, and the beam of electrons would then be directed to hit certain pixels on the screen. Well, the problem is that you can only direct them if they're all going the same speed. So you have to actually put it through what we call a velocity selector first. Okay, well, this is the velocity selector right here, these crossed fields. So you have electric field one way, magnetic field perpendicular to that, and so the only electrons that make it through are the ones that are going the right speed. And so those are the ones that are coming the right speed, and then you can deflect them where you want them to go. All right, so this is the idea of these crossed fields right here. And historically, this actually turned out to be very, very important because these crossed fields eventually led to actually the discovery of the electron. Because then they could actually figure out from that the velocities and the x and y components of the velocities, and from that they could solve to figure out what they knew the charge was the fundamental charge, and then they found the ratio of the charge to the mass, and that gave them the idea of an electron. Okay, so that was how the electron was actually discovered, was using these kind of crossed fields right here. We'll get back to an example of using this later on.